Hello friends, welcome to engineering tutorial. Uh, in the previous videos we have discussed about nodal analysis and some questions or circuit problems related to that. We have discussed around two problems related to nodal analysis. This is the third problem that we are going to discuss. So this problem is interesting because it involves both independent and dependent current sources. See here, this is an independent current source having 3 ampere, and this is a dependent current source. Okay, it is dependent on some other circuit parameter. See here, it is given 2ix, okay, the current value, and here the notation is given ix, which flows between node 1 and node 2. So it will be in the form of the nodal voltages V1 and V2. Okay, so like all the previous questions, first we have to write the KCL equations for each node, and then we have to convert it into nodal voltages. Here there are 3 nodes, 1, 2 and 3, so there will be 3 nodal equations, and we have to find out the nodal voltages V1, V2 and V3. Okay, so let us start with node 1. Okay, so here I am calling this current as I1, flowing through 4 ohm resistor, flowing from node 1 to node 3. Okay, and I am calling this current flowing downwards from node 2 as I2, flowing through 4 ohm, and I am calling this current as I3. We can assign current notations and directions arbitrarily as per our choice. Okay, I1, I2, I3 we have assigned, rest are all given in the question. Now let us write the nodal equations for node 1. In node 1, you see 3 ampere is flowing towards node 1, 3 ampere, this independent current source, 3 ampere is flowing towards node 1, and I1 and Ix, they are flowing away from the node. So here the nodal equation will be I1 plus Ix is equal to 3 ampere, constant. Now we have to convert these nodal equations which are in the form of currents into nodal voltage equations. We know that current always flows from a higher voltage point to a lower voltage point. Okay, so it is VH minus VL divided by the resistance between the 2 points. Okay, this VH is the higher voltage, VL is the lower voltage. So here also, if we use this concept, Ix can be written as, it is flowing from node 1 to node 2, it will be V1 minus V2 by 2 ohm, and I1 will be V1 minus V3 by 4 ohm, because I1 is flowing from node 1 to node 3. V1 is the higher voltage point, V3 is the lower voltage point. For Ix, V1 is the higher voltage point, V2 is the lower voltage point. So I1 will be V1 minus V3 by 4, and Ix is V1 minus V2 by 2, which is equal to 3. Okay, so now let us take the LCM. This is 4, of course. It is V1 minus V3 plus 2 into V1 minus V2 is equal to 3. So it is V1 minus V3 plus 2V1 minus 2V2 by 4 is equal to 3. So this becomes V1 plus 2V1, 3V1 okay, minus 2 V2 minus V3 is equal to 12. Okay, this is the first nodal equation that we got. Okay, 3v1 minus 2v2 minus v3 is equal to 12. Similarly, we have to get the remaining two nodal equations for node 2 and node 3. So now we have to write the nodal equation for node 2. Okay, first in current form and then in nodal voltage. So in node 2, you can see Ix is flowing towards the node, I2 and I3 are flowing away from the node. See, Ix is flowing towards the node, I2 and I3 they are flowing away from node 2. So it is here, Ix will be on one side and I2 and I3 will be on the other. This is the nodal equation. Now we have to convert it in terms of nodal voltages. So Ix is, as we have written earlier, V1 minus V2 by 2. Higher voltage minus lower voltage divided by resistance involved. I2 is flowing from 2 to ground, node 2 to ground. So it is V2 minus V ground by 4 ohm. Ground voltage is 0 volt, so it is V2 by 4 simply. I2 is V2 by 4. Similarly, I3, it is flowing from node 2 to node 3. It is V2 minus V3 by resistance involved, which is 8. So it is V2 minus V3 by 8. Okay, so let us bring all of them in one side. So it is V1 minus V2 by 2 minus V2 by 4. Here V2 minus V3 by 8, if we take it to the other side, it will become V3 minus V2 by 8 is equal to 0. Okay, V2 minus V3, when we took it to the other side, to the left side, becomes V3 minus V2 by 8. Minus V2 minus V3 by 8 is same as V3 minus V2 by 8. Now the LCM, so it is 8. So here it becomes 4 into V1 minus V2 minus 2V2 plus V3 minus V2 is equal to 0. Okay, so here it is 4V1 minus 4V2 minus 2V2 plus V3 minus V2 is equal to 0. 8 multiplied with 0, it becomes 0. That implies 4V1 minus 7V2, 4V2, 2V2 and V2 minus 4 minus 2 minus 1 becomes 7 plus V3 is equal to 0. Okay, this is the second nodal equation. Okay, 4V1 minus 7V2 plus V3 is equal to 0. This is the second nodal equation. Now we have to get the third nodal equation, then we can solve the three nodal equations to get the values of V1, V2 and V3. So now we have to put KCL at node 3 and get the nodal equation for node 3. So at node 3, if you see, I1 is flowing towards the node, I3 is flowing towards the node, 2Ix is flowing away from the node. Okay, I1 and I3 flowing towards node 3, 2Ix is flowing away from node 3. So it becomes I1 plus I3 is equal to 2Ix. Okay, now remember 2Ix is the dependent current source. So its value Ix, the parameter on which it is dependent, is derived from here. So Ix is V1 minus V2 by 2. Okay, Ix is V1 minus V2 by 2. So 2Ix will be 2 V1 minus V2 by 2. So simply it is V1 minus V2, okay, because 2 and 2 got cancelled. So let us convert it into voltage, nodal voltage form. So I1 is V1 minus V3 by 4, I3 is V2 minus V3 by 8, and 2Ix from here is equal to V1 minus V2, which we just calculated. So if we take the LCM here, be 8, which is 2 into V1 minus V3 plus V2 minus V3 is equal to V1 minus V2. Okay, so if we take it to the right side, becomes 2V1 minus 2V3 plus V2 minus V3 is equal to 8V1 minus 8V2. Okay, if we rearrange the terms, so it becomes, okay, if we solve it, comes 2V1 minus 8V1 minus 3V3 plus V2 plus 8V2 is equal to 0. Okay, this is the equation. Now if we solve it further, it becomes 2V1 minus 8V1, okay, it becomes minus 6V1, okay, minus 6V1 plus 9V2 minus 3V3 is equal to 0. Okay, if we divide it by 3, each of the terms we divide it by 3, it becomes minus 2V1 plus 3V2 minus V3 is equal to 0. This is the third nodal equation. Okay, so this is the third nodal equation. We divided each of the following terms, this equation, by 3. We got minus 2V1 plus 3V2 minus V3. This is the third nodal equation. Now we have got all the 3 nodal equations. Now all we have to do is find out the values of V1, V2, V3. Now it is a bit lengthy, I can understand, but this is the process, so we have to go through it. Okay, so we have got these 3 nodal equations, okay, from the 3 nodes 1, 2 and 3, where we applied the Kirchhoff's current law, and then we converted it into the nodal voltage form. Now we have to solve this. Now when you come across equations involving 3 variables, of course you will have 3 equations, it can get a little tricky to solve. Okay, now the first approach is, if your college or educational institution, it allows scientific calculators, then you can solve them easily in a matter of few seconds by going into the equation mode and selecting the 3 variable format. You just put this coefficients 3, 2, 3 minus 2 minus 1, 4 minus 7, 1 minus 2, 3 minus 1. You put these coefficients, you will get the result immediately. Okay, if scientific calculators are allowed in the exam in your educational institution, or for any other exam for that matter. Now if scientific calculators are not allowed and you have to do it by yourself, then there are a few approaches. First one is the variable cancellation method, which we used in the previous video related to nodal analysis, where we solved a problem of 2 variables, nodal voltages V1 and V2, and we solved it using variable cancellation method. But the most useful method is Kramer's rule. Okay, Kramer's rule. Okay, it involves converting this equation into matrix format and then uh, evaluating the determinant of that matrix and then calculating the value of the unknown variables. Okay, so here we are going to discuss how to solve the following system of equations using Kramer's rule. Now in my engineering mathematics section, I have a detailed video related to Kramer's rule. I have already posted that. You can check out that video. Okay, but here I am going to solve this equation using Kramer's rule. Okay, so these are the three equations. Okay, 3v1, 2v2 minus v3, 4v1 minus 7v2 plus v3 is equal to 0, minus 2v1 plus 3v2 minus v3 is equal to 0. Okay, so let us convert it into matrix format. You can note these equations down, because due to lack of space I have to go to this direction, so a part of this will not be visible. Okay, converting this equation into matrix format, we get 3 minus 2 minus 1, okay, or we can write it as 4 minus 7 plus 1, or minus 4 7 1 minus 1, both are the same thing. Okay, so let us go with 4 minus 7 and 1, and then it is minus 2 3 minus 1. So what I am doing is I am writing just the coefficients of v1, v2 and v3 in the matrix. Okay, now the three variables are the three nodal voltages v1, v2, v3, and the constants are 12 0 0, 12 0 0. Okay, first we have to evaluate this determinant. Okay, this determinant value. Okay, so let us determine the determinant of this matrix. Okay, 3 minus 2 minus 1, 4 minus 7 1, minus 2 3 minus 1. So it will be 3 into 7 minus 3 plus 2, minus of minus 2 is plus 2, is minus 4 plus 2 minus 1 into 12 minus 14, which is equal to 3 into 4 plus 2 into minus 2 minus 1 into minus 2. Okay, so this is equal to 12 minus 4 plus 2, which is equal to 10. So this determinant value is 10. Let us write it as this is equal to 10, del symbol, the determinant of this coefficient matrix. Okay, let us write it on the side. Now next we have to evaluate determinant del subscript 1. In here what we have to do, we have to replace this constant 12 0 0, this column, in the first column of the del matrix or the coefficient matrix. So in place of 3 4 and minus 2, we have to substitute 12 0 0. Okay, in place of 3 4 minus 2, we have to substitute 12 0 0. I have already explained this detail in the Kramer's rule in the engineering mathematics section. You please check out that video. Okay, they have explained in detail, so I am not going into minute details right now. 12 0 0 minus 2 minus 7 3, and here it is minus 1 1 and minus 1. Okay, now we have to evaluate this determinant. This is easy because here it is 0 0. If we go by this column approach, it will be just equal to 12 into 7 minus 3, which is 12 into 4, which is 48. So let us write it down. Delta 1 is equal to 48. Okay. Next, del 2. So this 1200 will be replaced in the second column. It will be 1200, and this will take the usual value 34 minus 2. This is del 2. This 1200 we have replaced it in the second column of the coefficient matrix. So again, this determinant, if we go by this column approach, it will be minus 12 into minus 4 plus 2. Okay, so this will be minus 12 into minus 2, which will be 24. Okay, so delta 2 is 24. Okay, next we have to evaluate del 3. So same thing, we will replace this 1200 in the third column. Okay, in the third column we will replace 1200, and here it will take the usual value minus 2 minus 7 3. This is del 3. So again, this will be, if we go by this column, it will be 12 into 12 minus 14. Okay, this is 12 into minus 2, which is equal to minus 24. So del 3 is minus 24. Now we have got all the values. Now we can easily calculate V1, V2 and V3. Okay. V1 will be del subscript 1 divided by delta, which will be 48 by 10, which is equal to 4.8 volts. Okay. V2 will be del subscript 2 by delta, which will be 24 by 10, which is 2.4 volt. V3 will be del subscript 3 by delta, which is minus 24 by 10, which is equal to minus 2.4 volts. Sorry. Okay, so here we have calculated the values of V1, V2 and V3. Okay, so this question, if this type of question comes in the exam, it can get a little lengthy, because first of all there are 3 nodal equations involved, because there are 3 nodes in the question. So first we have to write the KCL equation, then convert it into nodal voltage form, get the 3 equations, then if scientific calculators are allowed, then it will take around 5 to 7 minutes. But if scientific calculator is not allowed and you have to go and you have to solve it by your own, then it can take an extra 5 or 6 minutes. Okay, 5 minutes. But if you practice these type of questions more and more, your hands will get speed. They will be adjusted to different kind of situations, how to deal with different kinds of equations, and you will quickly figure out what kind of a method will be suitable for this kind of equation. For example, if for a particular question variable cancellation method, you think that variable cancellation method is good, then you can quickly apply that method, and for some, Kramer's rule can be used. Okay, so these type of questions can get a little lengthy, so please do not lose patience. Carefully solve each and every equation, apply KCL very carefully at each and every point, because one single mistake can cost you the entire question. Okay, so I hope you like this video. And please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.